Thank you, Itzhak, for a very interesting talk. And our next speaker is Omri Danziger from Foresight Automotive. And he's going to talk about consistent pixel matching between different cameras using individual temporal updates. Thank you.
Okay, so hello. I'm going to present a method on a consistent oriented method for pixel matching between different images. A few words about the company first. So Foresight focuses on vision solutions for stereo cameras. And if you can see here in the image, there is also visible light cameras and thermal sensors cameras. The subject is going to be 3D reconstruction with stereo matching. So to put it shortly, it involves using two cameras that take pictures simultaneously and then matching pixels between them and triangulating them with previously known calibration in order to create distance estimations with triangulation. So one of the difficulties when doing something like this is consistency over time. Because even relatively accurate results can have some sort of error distribution. And when seeing the results over time, they can seem to jitter up and down, and they can seem to jump between decent solutions. So here is a short video, for example. We can see that the far areas in the image that are marked in blue seem to shake over time. And this is a phenomenon that is the opposite of consistencies. So the method here will attempt to improve this. So there are existing solutions to try to mitigate this difficulty. One of them is to estimate where those areas are and to filter them out. The problem is that you may filter out areas that are otherwise okay to use. When training to avoid this issue, it's hard to augment the exact phenomenon from motion because of the occlusion and specific elements that happen in actual motion. It's hard to augment those spatially on the image. And so the other method to address it is to use temporal models, which pass on previous decisions onto the next time frame. These are often based on some form of transferring the previous estimation, sometimes through SLAM. SLAM might be difficult in environments that include a lot of dynamic objects, and sometimes include motion estimations, such as disparity change blocks, which are unique blocks that might be computationally heavy and otherwise difficult to train. So the intuition for the temporal model I'm going to show it can be visualized when imagining a baseball coming your way. So if you can see it initially when it is far away between both of your eyes, you can see that as it comes closer to you, it also moves with the left eye and with the right eye. Tracking it with both eyes can give you the position of the ball relative to you at any point of time, even without direct matching between the eyes after the first time you see it. And a more formal way to address it can be seen in this graph. Basically, every box here represents an image. And the bottom two represent the images we want to match with previous knowledge of the matching we did in the top two images. We estimate the optical flow in each camera from the new point in time to the previous point in time, and combine the optical flow with the previous disparity estimation to create an indirect estimation between the two new images. So basically, we combine a path with the new left image to the previous left image, to the previous right image, to the new right image. And all this is done with existing optical flow blocks and simple remap operations. One of the issues when addressing something like this is occlusions. Generally, disparity networks tend to give reasonable solutions to those occlusion areas, which means areas that we can see from the left image, but not from the right image. In this specific method, it will be more problematic to work with those areas because if something is blocking the view from one of the cameras, we can't track it with the optical flow. So in order to improve this method, the mask is also passed throughout the optical flow combination path, creating a mask of occlusion from all the cameras so that we can only track the objects that were visible throughout the path. And this is an example with real images, like we've seen before. So we calculate the optical flow from the left image, from the right image, and the previous disparity map. And we create what is on the bottom right, which you can see has the occlusions filtered out. They are in white. And the rest are created by updating the values from the previous disparity. So this is an example video I'm going to show the results on. It's pretty straightforward. There is a dynamic object in the image. Of course, this is the vehicle we're driving behind. And okay, so this is the result. Generally, on the top, we can see what happens if we estimate a new disparity every frame. And on the bottom, we can see what happens if we pass the optical flow, if we pass the first estimation onward with the optical flows. So if we focus on the problematic areas, such as the trees in the background now, we can see they are significantly less shaky, significantly less jitters in those areas. Here is an example when replacing the disparity method previously used with a pretty inaccurate semi-global block matching method from OpenCV. So this is to show that the method can easily work with replacing the optical flow blocks. And anyone familiar with this method will know there are sometimes failed matches, which can be marked in blue in this disparity, in these depth maps. And we can see that those failed matches are very shaky over time, but when we pass on the first estimation, we avoid this issue. Here is another example with a bumper. This is the video, and it's to show that the top of the image, after passing on the first result, cannot estimate the sky and the top area of the image because they did not exist in the first image. Here is an example of we have a fence. We're driving towards a fence right next to the pole here. So a fence is a problem because it sometimes can be relatively accurately predicted as a wall and sometimes as transparent. So on the top we can see that the model shakes when with regards to this decision over time, and the bottom one maintains the previous solution. So to summarize, we mentioned the consistency-oriented models, what problem they are trying to solve, how tracking optical flow between two cameras can help solve this issue with already made blocks, and how accurate we can get the stability between these results over time when passing them over to indirect flow. So that's it. Any questions? Thank you.